Okay, so the second part of this section is just talking about like growth and decay and modeling with exponential growth and decay. And so it says if you have a times b to the x, which is kind of our go-to function for exponential functions, if a is greater than 0 and b is greater than 1, then the function is increasing and is exponential growth. B is the growth factor. And if a is greater than 0 and b is less than 1, then f is decreasing and is exponential decay. That's kind of like what we talked about yesterday, whereas this is growth and this is decay. But there's other factors that come into that, like what if a is not greater than 0? That affects things, and so it's kind of a little tricky sometimes to do this. So really just kind of two things we're doing on this video. It's going to be pretty short. One, state whether the function is exponential growth or exponential decay. You got to be really careful on this. I say think about what's happening here, because like this doesn't fit the pattern a times b to the x because this is negative, but think about what a negative exponent is. So I automatically think about this as 3 to the 2x on the bottom. So what's going to happen on this, negative exponent goes at the bottom. If you pick bigger and bigger numbers for x, that's going to become a smaller number, right? And I always say if you aren't sure, pick numbers like 10 and 100 and 1,000 and see, is it going towards like infinity? Is it growing? Or is it going towards 0? Is it decaying? And on this one, because like if you keep picking bigger numbers here, right, you're going to keep getting a fraction where the denominator is smaller, which means that this is actually a decay function. Even though 3 is bigger than 1, because this is a negative exponent, that's what makes it a decay function. What about number 2? What do you think on that one? So let's think about this. Again, if you think about it, I don't know. If you think about this as e to the negative x, wouldn't that be the same as this? Kind of understanding where the exponents come from. That's why it's in the bottom. That's the same as 1 over e to the x. Your book talks about limits, and limits is just what happens as x goes towards infinity or towards negative infinity. That's what a limit is, so don't let that freak you out too much. To me, it helps me look at it like this, but if you can't tell just by looking at it, pick like 10 and 100, and you'll see whether it's getting bigger or smaller. I think it's getting smaller again, because if you pick 100 in there, e to the 100th, right? 1 over e to the 10th power is a really, really small decimal. So this one's also getting smaller. It's going towards 0, which means it's decaying. Okay? So you just have to kind of think about those. The other thing that I want to talk about, which we're going to keep talking about in this chapter, is applications. And one application is a logistic function, talking about population. So it says population in Ohio can be modeled by this function, where P is the population in millions and T is the number of years since 1900. Really important to read what this is saying. So it's saying the answer that you get is millions. So if you get an answer of like 7, it would be 7 million. And T is the number of years since 1900. So for part A, it says how many people were there in 1950? Well, you're not going to plug 1950 in for T. If T is the number of years since 1900, you would plug 50 into that. And that's a big calculator question. So if you're going to type this in all at once on your calculator, you must put these parentheses down here. You could also do the bottom and then divide by 1279. If you have a calculator, I hope that you'll actually try to do this and see if you get the right answer. And if not, maybe in class tomorrow, you can do that. So I'm going to divide by 1 plus 2.402 times e to the negative 0.0309 times 50. And I get 8.45689.6. I guess I'll round that to 7 because it's 666. That's million, right? So what's fantastic about this, because it says in millions, that's 8,456,897 people, or about 8.5 million if you want to say. So that's just reading it and understanding the problem. But part B says, when would the population be 10 million? Well, the population's growing, and so it's definitely after 50 years. And there's definitely other ways to do this that we'll do later on when we remind ourselves how to solve these equations. But right now it's kind of a guess and check method. So it's more than 50, so I say let's just try like 60 and see what happens. So I'm going to plug in 60 years. And what's fantastic is I already typed this all in before. So I just have to go up there and change it to times 60. And I got 9.29. So I'm going to go 65 years. Oh, 9.67. All right, I thought jumping to 70 was too much, but I'll jump to 70 now. It's an exciting math video, right? 10.02. So you could check that 1969, I guess, but it's 9.95. So I'm going to say in 1970. Okay? So we'll practice that in class tomorrow, and there you go.